Hello and welcome to today's webinar on a short optimization tour through transparent and fair machine learning, presented by Professor Dolores Romero Morales from Copenhagen Business School. Thanks so much for joining us for the first academic webinar of 2025. Our academic webinar series is designed to highlight the innovative ways researchers and educators use Gurobi to tackle complex problems, advance optimization techniques, and inspire new applications in operations research and data science. These webinars are the cornerstone of our mission to empower learners worldwide and to help democratize optimization education, offering practical insights that resonate across a diverse audience of problem solvers. My name is Lindsay Montanari, and I lead the academic program here for Gurobi. So before we get started, I'd like to share just a couple quick notes to ensure you have the best viewing experience during today's webinar. First, for optimal viewing, please take a moment to click on the gear icon at the bottom of the presentation screen and select 1080p. Dr. Romero Morales will walk us through some detailed models and figures, so a higher resolution will enhance your experience. Second, we encourage you to ask questions throughout the webinar. You can do that by using the Ask a Question tab below the presentation. We'll address as many as we can during the final 10 to 15 minutes of the session, and along with Dr. Romero Morales, we're fortunate to have Matthias and David from our technical team here today, ready to dive in and assist with any questions at the end of the presentation. And finally, we value your feedback. At the end of today's session, please take a moment to rate the talk and share any comments you might have. Your input helps us tailor future webinars to topics that matter most to you and the academic audience. So as part of the academic webinar series, I wanted to share just a little bit about the academic program before we kick off. At Gurobi, we've always been committed to supporting academia, and one of the ways that we do that is by making sure that Gurobi licenses are always free for academics and recent graduates. If you're a student or a faculty member, all you need to do is visit gurobi.com and head to the academic section. There, you'll be able to easily register for your Gurobi account. You can download free, full-featured academic licenses, and you can get started with Gurobi today. If you're a practitioner viewing this session, you also are welcome to try out the full solver. Simply visit gurobi.com and click on the red free trial button to start using Gurobi today. So we've been hard at work on a range of open educational tools and resources for students and instructors to use to learn and teach Gurobi and mathematical optimization. You can check out our free Udemy massive open online course, our burrito optimization game and teaching tools, our example and Jupyter Notebook libraries, and so much more at gurobi.com/learn. So now I am delighted to introduce Professor Dolores Romero Morales. Dolores Romero Morales is a professor of operations research at Copenhagen Business School. She specializes in data science, supply chain, and revenue management. Her research focuses on explainability, fairness, and visualization in data science, environmental and robust solutions in supply chain optimization, and large-scale network models in revenue management. Her work's been published in leading journals such as Management Science and Operations Research. She's collaborated with top companies like IBM, SAS, and KLM, and she's also earned recognition as an honorary SAS Fellow. Previously, Dolores was a professor at the University of Oxford and holds a PhD in Operations Research from Erasmus University in Rotterdam. Please join me in welcoming Dolores Romero Morales. Dr. Romero Morales, over to you to introduce your important research and guide us through transparent and fair machine learning.
First of all, I would like to thank Lindsay from the Gurobi Academic Program, and I would like to extend this thank you to all the colleagues from such a program. And I would also like to thank the audience for coming today. I'm going to show a few papers, a few slides about what we do in our team in respect to transparent and fair machine learning. I'm going to be showing you some visualizations, but I hope that you will also have some screenshots of some of the mathematical models that we work with. At this point, I would like to thank the team. There are plenty of PhD students, former PhD students across Europe, and even, at the other side of the water. So thank you to them. You are seeing this presentation today. So first of all, I'm going to give you a little bit of an introduction about transparency in machine learning. And then we will move on to fairness. So you can see that I have separated these two. But at some point in one of the slides, I will put them together and I will show you what we do nowadays, combining these two and how important it is to combine the two of them. The presentation will have a third part, which is about counterfactual analysis, something that has become very popular nowadays. And I will show you a recent review that we have written and some new ideas and food for thought at this respect. So as I said, I was going to start with the importance of transparency. But first of all, let me say to you that obviously machine learning is impacting the way we take decisions. And there are plenty of examples in which we like to draw on these machine learning models to enhance the decision-making models that we have, and to make the better use of all this data that is available out there. In these machine learning models, there is plenty of optimization content, and I just have there 2 citations, but I could have many more. So the paper from Gambella is one of the paper, et al. Is one of the papers in the European Journal of Operations Research, in which they basically cover, say, different aspects of optimization in different machine learning models. So what it has been required for quite a while is that in certain areas where we are applying machine learning models, we require that these machine learning models are not only accurate, so not only having good predictions, but also being transparent to the user, so to understand how the model arrived at the prediction. And this has been, for instance, required in areas such as credit scoring, but these requirements are being rolled out more extensively to, in general, algorithmic decision making. And for instance, the European Union is pushing some of this regulation, and I'm giving you a couple of references over there. This, in parallel, we can see that there is a whole range of tools, XAI tools, that they are called explainable artificial intelligence tools, that are trying to provide transparency to these machine learning models. Sometimes they are basically a second step, a two-phase approach in which you construct the model and later you explain the model. We will talk about this a little bit more later on during the presentation. So I told you that there is plenty of optimization when we try to build machine learning models because we are optimizing errors. But when we are imposing not only accuracy, but also transparency, there is also plenty of optimization models that we can, build, because it's clearly a trade-off between these two objectives. So on one hand, the accuracy, and on the other hand, the transparency of the machine learning model. So I've been talking here in the previous slide about transparency, and what I said simply is that I would like to understand how the model makes decisions, but I haven't given you a proper definition. And I will not give you a proper definition because, as I said in my slides, it depends on the user. So what is basically acknowledged is that a linear model or a model based on rules is to be understood more easily than if I have a sophisticated model as a NextGPUs, in which I have an ensemble of many other models, or even worse, a deep learning model in which I have many, many layers and in which I have nonlinear transformation of the original data. So therefore, people talked about, say, white models, gray model, black box models, and so on. Even if I depart from a linear model or a rule-based model, which I said that is easy to be understood, transparency, say, is lost if I would have, say, a large model. And when I call a large model, it would be many features in a linear model, or many rules, or say long rules in a rule-based models. So therefore, it's important that even if we have as a starting point an easy to be understand model, that this model is, say, small, and therefore there are methodologies that are very well known in the community, such as the lasso or such as the best subset selection model, in which we try to basically shrink these models. And there is plenty of optimization behind these models as we are selecting, say, feature, or as we are shrinking, say, the coefficients of a linear model with a regularization term becoming, say, a weighted approach to the existing machine learning model. So even though I'm not going to give you a definition of transparency, what I would like to tell you is, say, different ways in which we can achieve transparency. So the first way that I'm having here is, say, to build, as I said, these structures that we seem to be finding easy to understand, such as rules. And an example here of a review paper that we wrote a couple of years ago is basically trees. So to make decisions with classification and regression trees. So in this case, we have rules, but they have a hierarchical structure. So in this paper, what we do is to acknowledge that recently there has been a lot of attention from the optimization community to build these trees in an optimal way. So as opposed to all these heuristic approaches that basically were popular in the past. So these tools, these optimization tools are based on, say, integer programming, in which we route the individuals in the tree using binary decisions, or we have also continuous optimization approaches, so in which we to encounter an individual at different leaf nodes of the tree with a certain probability. And this probability is defined by a cumulative density function. So these are two of the most popular tools to build optimal trees, and we also have others such as constraint programming and etc. Another way of, say, enhancing transparency is to select, say, small models, as we mentioned before. And here we use the word sparsity to refer to selecting a few features from a model. This sparsity could have, say, a structure. And here I'm showing you a categorical variable. And this categorical variable, normally in linear models or in tree models, this categorical variable will be represented with, say, a dummy for each of the category. But you could imagine applications in which you would have, say, many categories, and then therefore you will have many dummies with each of them having a coefficient, so it's not very easy to interpret. So what we have done in a number of papers is to say, well, what if we reduce, say, the complexity of these categorical variables by clustering their category, and therefore having an alternative representation of the variable in which we have, in this case, just a binary representation with two a set of categories. So the red categories will share, say, a coefficient in a linear model, and the blue categories will share another coefficient. So in this way, we don't need to interpret all the coefficients of all the dummy variables. We just need to interpret in this way, say, the coefficients of the new representation of the variable. This is even more complex if I have what we call a hierarchical categorical variable. And you can see there, for instance, the states of America, which can be grouped at different levels of granularity. Therefore, I have different levels in this tree. And if I go all the way to the top, then all categories, all states would be, say, all sharing the same coefficient, therefore is equivalent to the variable not being, say, in the model. I can again group the categories in this variable, but if I do so, I will need to respect the hierarchical structure. So therefore, what I have here is that I need to select a subtree of the initial tree, and the subtree will be, say, a reduced representation of the original categorical variable. If I do so, I end up, for instance, having, say, in a linear regression model, in which I'm minimizing, say, the square of the residuals, well, I will need to incorporate not only the decision of the coefficients in the linear model, but I would also need to incorporate the decision of which substrate I will select, and I do that with 0, 1 variables, and this is what we did recently in one of the papers. So you can see that actually bringing a new structure to the classical OLS optimization model that we have. Let us go to a little bit of a more complex data. So here we are not dealing with, say, numerical and categorical data. Here we are dealing with functional data. So some of my measurements could be functions. So say that you are, for instance, having sensor data and that you are having the measurements from those sensors. And what we try to do in this paper is to say the following. Instead of having this functional data straight into the model, could I select, say, parts of this functional data, so intervals of this functional data, in which I'm assuming that the contribution of that interval towards my machine learning model is constant. So you are detecting basically which are critical intervals for this kind of data. So what we did is to bring this selection of these critical intervals to our classification and regression trees that we saw before, and then you end up having, say, again, to select, say, parts of this functional data, so you end up with a more sophisticated formula of sparsity that we did model in our objective function. So I hope that you have seen different forms of sparsity for different types of data. And now what I'm going to show you is another way of imposing transparency. So in this way, I impose transparency by building, say, a surrogate interpretable model or transparent model to the output of an original black box model. So let me show you here on the left say the output of one, say, random forest, or it could be an XGBoost. So a model with in which we combine many trees. So we know that if we combine many trees, it would be difficult to say to visualize the output. But what if I could rewrite this tree assemble as a one single tree, which hopefully is a short tree. So therefore, it's much easier to say, to understand which variables are impacting my model. So this is what we do in this paper. So we have a sophisticated way of selecting which are important thresholds to my trees in my ensemble. And then, so the dark colors will represent which are, say, these thresholds that are very important. The light colors will tell me that they are less important. And with this information, I go ahead and then I build an optimal tree, which is short, as I said. And so we end up having a simplified model, which tries to resemble the predictions that I did with a more complex model. By the way, in this paper, we also end up with a discretization of the variables that you can bring to any of your favorite machine learning models. And this discretization basically will allow you to use some of the optimization models for machine learning that they require discretized data as opposed to any type of data. So this is what I wanted in short to present about transparency. So how, say, you can, with optimization, bring many forms of transparency into the training of your model. Now, what I'm going to try to do is the same with fairness, and we will put all together in a few slides. So I think you have probably been exposed to some of these events in the news. So basically with the, say, the boom of AI tooling, we will think, what we also see is that sometimes the use of the AI model does not take into account some sensitive groups that you may have in your data set. So we see here examples about, say, a recruiting tool in some companies in which there is discrimination in terms of gender. We also see this in terms of healthcare at the top article to the right. Then at the bottom, we have, say, to the left, we have an algorithm that it was, say, used in the Netherlands for social benefits and how it was discriminating in terms of income. And to the right at the bottom is a typical data set that is being used a lot in fairness in machine learning research, which is the COMPASS data set that again, in this case, is about giving parole to individuals and how the algorithm is, say, discriminating certain racial profiles. So what happens then in research is that we tackle this fairness by trying to basically protect these sensitive individuals. And as I said, these sensitive individuals can come from different reasons that I have mentioned in the previous slide. We try to protect them, say, for being unfairly treated by the algorithm. How do we do this in optimization? Well, this may end up being, say, a new objective, or it may end up being, say, an additional constraint that you have during the training of your model. Obviously, the shape of this objective or the shape of this constraint will depend on which fairness metrics we will use. And we have to be aware that there are many, say, fairness metrics. And by the way, they will also contradict each other. So you are building a model for a given fairness metric, and if you want to incorporate another one, say they may give you different results, the model. So here what I have is a visualization of, say, one data set in which I'm using supervector machines as my machine learning model. And you know the supervector machines will say make decisions based on scores. And so if you have a high score, you will go to the positive class. If you have a low score, you will go to the negative class. And you can see that for the, say, protected group, the one I think I have to protect, I can see, say, the distribution more towards the low scores, while for the non-protected group, I can see that the distribution is more towards the high scores. So if I were to make predictions with this plain supervector machine in which I have not incorporated any fairness constraints or objectives, then I will probably be discriminating, say, the protected group because of this distribution that I'm having of the scores. So what we try to do is we try to address this in the literature, and in our case, in our group, what we have done is we have written a couple of studies in which we impose fairness by modeling a distance between, say, distribution, for instance, of scores, as you saw before. So this is the case in a paper in which study supervector machines, and in which we studied these two distributions that you just saw of the supervector machine scores. And then we impose that these scores that you can see over here, that the scores for the sensitive group and the scores for the non-sensitive group, we try to bring them closer together thanks to the Wasserstein distance. So once we do that, so the optimization problem that we need to solve is not only on, say, the alpha decisions coming from a standard supervector machine, but we also need to optimize the optimal transport decisions coming from the Wasserstein distance that we have decided to use. Now you may wonder, why did we decide to use the Wasserstein distance? And the reason to do so was motivated by the fact that if we incorporate the Wasserstein distance into the dual formulation of the supervector machine, and we do a few small calculations, we end up rewriting the problem as a supervector machine with a new kernel in which you have the old kernel, but you also have a correction due, say, to the thanks to the optimal transport decisions, and also the, say, the split between the sensitive and the non-sensitive group. So the optimization here could be done, say, in an alternative alternating procedure in which I optimize first for alpha and then I optimize for pi, for the pi's that we have here. So we did this in our paper, and then you can see that, again, another, say, trade-off, in this case is trade-off between, say, accuracy and fairness. So again, reiterating that if we were to incorporate fairness, there is a multi-objective problem behind. And then what we try to show you here is this trade-off. So there is, I would say, a rather flat area here in our frontier, in which if I try to improve my versus time distance, basically my accuracy out of sample is not affected. So this is a message that we like to present in our team, which is the same message that you have when you are trying to impose sparsity in models. Sometimes you have this area in which you gain in the second objective that you are optimizing without losing much in your accuracy. Obviously, if you would like to bring your fairness close to zero, so meaning that your distributions of the scores in the sensitive and in the non-sensitive group would be almost the same, that would be basically bring your accuracy down. I'm talking about supervector machines, I'm talking about versus time distance, but just to give you an idea that I could be doing this in different, say, machine learning model. In this case, I do lasso regression, and that the distance could not be taking care of the whole, say, distribution, but maybe the distance only wants to take care of the high predictions, because, for instance, you are only caring about GPA predictions of students when they are going to be admitted or not to university. So then you are only looking at the right tail. And here what we are trying to make sure is that the proportion of individuals from the sensitive and the non-sensitive group, this proportion is similar. And then we end up having, again, say, a trade-off between error and between unfairness. And I just wanted to point you out here that this trade-off is actually, it depends on the parameter of the lasso model, meaning that actually the three objectives are interacting with each other. So sparsity, fairness, and accuracy. I would like to bring you here the same message, but again, yet with a different machine learning model. So here we are working with an ensemble of trees. The trees can come from a random forest, or they could come from, say, just a collection of stamp trees that you have built with an existing, say, subset of the data. And what I do is I train the ensemble, so I train the weight that I give to each of these trees in such a way that I, again, have a trade-off between, say, the error, my measure of fairness, which in this case is, say, my accuracy in the sensitive group, and sparsity. So actually, I impose directly sparsity on my ensemble model, something that you could not do so easily, say, in a random forest when you are building a random forest. So what you can see over here is that I have a parameter that basically gives, say, more weight to the unfairness or less. And what you can also see is the black line of the random forest, in which, you know, I run a random forest with a limit on the number of features. So our own ensemble, which is not in black, our own ensemble can give you a better error. And actually, our own ensemble can give you a much better unfairness. That's what we are seeing in this data set, which is actually the COMPASS data set that I mentioned before. Even more, our own ensemble can make you visualize that actually the features that you are selecting in our methodology would depend on the level of unfairness that you are prepared to have, meaning that you have, again, this interaction between sparsity and fairness, and that the features that you are selecting should be selected taking into account how much unfairness are you prepared to have. This is just one more visualization to make you see that our methodology will allow also to visualize the impact of variables into the model. So you not only are able to select features, but you can also see visualize the impact of those features in your classifier. Now, in this very last part of the presentation, what I would like to move is to contrafactual analysis. Now, what I would like you to see is that we are changing gears. So now the machine learning model is already built. And what you are going to do is to see how that model is impacting a given individual, and if it's impacting a given individual negatively, then you will try to give an explanation to that individual. So this is a tool that has become very popular in XAI, and actually you can see here that one of the main drivers of this XAI is actually DARPA. So what do we do in contrafactual analysis? I told you that my machine learning model is now given, so therefore it has been built, and for the ease of the presentation, I'm just going to assume that it's a probabilistic one, but most of the models that you are familiar with, they will be probabilistic ones. So I have a probability of an individual to belonging to the positive class, so I'm assuming binary classification. So positive class is, I'm assuming that is something good for the individual, so be given parole, or say be given a good credit score. And then what we do is we are going to construct explanations. So we are going to construct new instances. So what I would like to have is also a function that will measure the cost of perturbing, say, instances. So that's another piece of information that we have. Now, we said that we are going to have an instance. So x0 is going to be that instance that is actually, say, negatively affected by the algorithm. So say that it has a low probability of being in the positive class. So the P for this instance is low. And what you would like to do is that the P is a higher one. So you are going to construct a contrafactual explanation. You are going to construct a new instance. Yeah. So X is going to be our decision variable now. And how do I construct that X? So what we are going to do is we would like not to cost a lot of effort for me to move from x0 to x. Yeah, so a low cost. And because it's an explanation for me to enhance my probability of belonging to the positive class, what we would like is a high probability of this x. And because we are minimizing, so the only thing that we have done is to put a negative in front, and that's it. Yeah. So we would like to maximize the probability, so minimize the negative probability. And obviously, we will have constraints. Yeah, so certain features would not be possible to move. For instance, gender. I would like to put bounds to the movement in other features, so it would not be, say, reasonable that I increase my salary, say, for next year by 50%. So we put boundaries. Yeah. But you may have other type of constraints that you want to model over here, like the structure of categorical variables and other things. Now, so this is clearly, yeah, an optimization model, and I will show you in the next slide that there have been quite a few colleagues recently working in this optimization. But let's put a little bit of more structure. So normally the cost function will include a dissimilarity. So how far, say, how dissimilar is the x0 to the contrafactual, and we can measure this with an LP norm, but maybe we have functional data and we need a more sophisticated distance, or maybe we want to have a symmetric cost. And so I've put there other references. And we also have a complexity. Because if I have to say make an effort to change my current features to enhance my probability of being in the positive class, then it may be easier not to focus in too many features. Yeah, so reduce the number of features that I need to change. So say I focus on my salary and I focus on my debt, and that's it if I want to improve my credit score. So yes, we can measure that with an L0 norm like we did before when we were trying to pursue sparsity. So this ended up being the usual two terms that are in the cost function. And for the probabilistic part, this is, we have done all the work in a paper that you will see in a few seconds. This probability can be rewritten as an increasing function of a score for many of the classifiers that you are familiar with. And this ends up being, say, to find a contrafactual explanation. So to find this X ends up being the minimization of a dissimilarity and a complexity. And if you want to find Pareto solutions, that you combine them through a linear term, imposing, say, a bound on the second objective, which is your probability, and that bound ends up being, say, the score of the machine learning model that you impose, say, a lower bound in that score, and still with the feasible region that we were talking about before. So what we contribute here to the literature is the fact that the literature has been focusing on, say, looking at every individual by itself. So every X0 gets their own contrafactual. But we take a stakeholder view, and then we try to give, say, explanations to a group of individuals. Why is that important? Well, the first reason is because you may have linking constraints. So for instance, if you want to make sure that you are not unfair, you may need to link, say, the problems that you are solving for individuals that, say, only differ on the sensitive information. You may also want to basically tell the stakeholder which are the important variables when you are constructing contrafactual explanations. Therefore, the selection of these features, they need to be done in one single model. You may want to, say, provide a diverse set of contrafactuals, and therefore that problem has to also be solved with one single model. Or you may want to choose, say, key individuals that become your contrafactuals for a group. So what is happening is that the literature is most of the time solving location problems in which you locate, say, where the contrafactuals are. And what we have is models which, in addition to these location decisions, so where the contrafactuals are going to be, we also have allocation decisions. So why do we need allocation decisions? Because, for instance, take the case in which I am, say, finding these key individuals that would become, say, contrafactuals. I need to decide not only the location of these benchmarks, but also who is going to be allocated to those benchmarks. So we have studied these models in a PhD dissertation that was defended recently, and I'm just going to show you, say, some of these mathematical optimization models and their output. So in this case, we are studying the case in which each individual is going to get their own contrafactual, but there are, say, linking constraints, and in this case the linking constraint is because I would like to select what are the features that will be allowed to be perturbed for all the individuals. So therefore I have this say regularization term that will take care globally of the features that I'm choosing. And what I hope you can see on the left is that now, depending on the weight that I give to this regularization term, I will select more or fewer features. And then the features that are selected you can find on your right. So I could select 2 features, or I could select 3 features, depending, say, on how much, say, I would like the trade-off between, say, the size of the perturbation and the number of features that I'm allowed to use. So in this case, the selection of the features has been together. Let me show you one more model in group contrafactual analysis, and this is the one that we have mentioned, in which I select benchmarks as contrafactuals, a few benchmarks, and then therefore there is the location decision that we had before, but there is also the allocation decision Y, in which I allocate, say, an individual to its explanation. So you can see that in this case, this resembles to what we do, say, in clustering, in which we have, say, an individual, and we would like to be very similar to that individual. So we are measuring, say, the dissimilarity within the cluster. But what we have done is to enrich this model with a constraint that is coming from the fact that you would like the contrafactors to have a high probability to belong to the positive class. And in this case, this constraint basically reflects say, a linear model in which I'm measuring this probability, say, with my scores being linear. Say, for instance, the supervector machine could be one of these models. So if I apply this model, what I would have is for 3, allowing 3 benchmarks, I will have the benchmarks here. I will have the second benchmark over there, and I will have the second benchmark over here. And what this heat map is representing is which individuals would like to be allocated to this contrafactual, and similarly, which individuals would like to be allocated to with this contrafactual, and to the third clusters the same. So what you can see in this case is not the perturbation, but the actual value of the features. And I hope it's clear to see that the features, they do resemble to their own contrafactor. So coming to the end of my talk today, I hope that in this short presentation I've been being able to show you some mixed integer nonlinear programming formulations in which we try to model the trade-off between accuracy, explainability, and fairness. I hope that in some of my illustrations I've been able to show you that, you know, with a mild loss in accuracy, I can have substantial gain in explainability and in fairness. Today we were doing machine learning models, but actually the community is also taking out these tools to solve, say, OR problems. And in particular, we are dealing in our team with benchmarking applications in which we are studying, say, explainability and fairness questions. I hope that you can see that I've shown you some typical models, for instance, in facility location, in clustering, cluster analysis, in which what I have done is to bring novel elements, such as novel constraints to these models. So therefore, there is food for thought, say, to develop algorithms specific for these new kind of problems. And in general, I have tried to show you that sometimes what we can do is, say, to enhance the scalability of models. For instance, in our tree assembles, we do that by building surrogates of the actual 0-1 error. We do the same in our optimal trees. We bring continuous optimization in which we avoid having 0-1 variables for our individuals, but there is much, much more scope, say, for the optimization community to contribute to the scalability of the techniques in which we incorporate explainability and fairness. And with this, I come to the end of my talk. I thank you very much for your attention. I will be happy to answer questions you have. And if I don't have today the time, you have all my coordinates over there. Thank you so much again.
Thanks so much for joining us today, and a special thank you to Professor Romero Morales for this webinar topic highlighting how optimization is used in transparent and fair machine learning. Now we've got a couple minutes left for a Q&A, and I'm going to turn things back over to Dolores and members of our technical team, Matthias and David, to guide us through audience questions. Thanks again.
Hey, hello again. So we actually have quite a few questions that came in during the presentation. So thanks for the presentation. First, Dolores. And I guess we start with the one from Nicolais. That is, when you compare the distributions of different groups, for instance, measuring the distance between them, do you know these groups a priori?
Thank you so much for the opportunity again, and thank you so much for the question. Yes, when I was talking about fairness today, I was assuming that there is, say, sensitive attribute that I know which one it is, and that I'm going to try to avoid, say, discrimination with respect to that attribute. So yes, the divide between the sensitive and the non-sensitive in the slides I was presenting today is known in advance. You may also want to construct a machine learning model that is robust against, say, possible unfairness, where you have to, say, make a combinatorial search of what could be, say, the possible sources of unfairness, the possible sensitive attributes. And as I said, that would bring you some combinatorial structure into your optimization model, because you will need to make the search across these possible sensitive attributes. Thank you for the question, which is a very appropriate one.
I'll read out another question. I'll pick this one. How large classification forest or neural networks can you handle with these methods? So a question about the size of the data.
Yeah, so I cannot give a general answer. So it really depends. For instance, in the paper in which we were trying to do explainable fair tree assembles, those are, say, lighter models. So what I tried to say during the presentation is that we don't have 0-1 variables to detect whether an individual is correctly classified or not. So we have a surrogate variable which is continuous. So we took away the say the binary decisions from the observation. We still have the binary decisions from the selection of variables. So there we can handle much larger trees. For instance, when we do counterfactuals for tree ensembles, which we also do, it is true that we need to have, say, a couple of hundred trees because otherwise, the computational time basically grows very rapidly. But as I said, it depends on what tool I'm using throughout my presentation.
Mm-hmm. Okay, a slightly related question from Maxime is whether the features are self-taught or introduced by...
Yeah, so I'm assuming that I have a data set, right? So somebody gave me a data set. There may be, there are, say, features I would not like to use, but be careful, because these features actually may be correlated to other features in the data set. So although you may say, hey, I don't use that feature, and I delete it from my feature, it may still be indirectly used in the model because of the correlations. So if you think about income, and if you think that you don't want to use a model that has the variable gender, fine, but it will be correlated, for example, with the amount of hours that the person will work, because we female members of the community tend to work fewer hours in general than males. So I understand that you may want to screen and say, well, I'm very, very against the use of these features, but yeah, unfortunately, they may be there indirectly.
Yep. A question from Elias, maybe I don't know, there's probably more details in the papers about the origin of the data. Where is it coming from, the data that you're using for the different...
The data I presented today, it's all
publicly available
data, and actually the source, the code, it's also available open source. So we try to use that.
Mm-hmm. Then we have a teaching related question from Carolyn, whether you have found any approaches in transparency effective for teaching new students about machine learning.
I bring these topics towards the end of my course. So I tell them about the importance throughout the whole course. I don't have a whole course on transparency, but every time I present a tool to them, I try to basically present, say, the trade-off. I'm in a business school, so I'm really obliged to talk about transparency, not because of regulation, but also because, the level of, say, the person at the other side of the table may not be very quantitative. So I have always tried to tell them, students, about trade-offs. Our whole research on machine learning started with super vector machines, which is, they are not transparent at all. But we have done quite a few papers in which we try to make the output more easier to understand. So I always try to tell the students that we do say we make our mathematical optimization more complex to ensure that our machine learning model is more, it's less opaque. Yeah.
Mm-hmm.
Nice. Another question from Inga. So what guidelines can you give to design an a quick converging cost function? So what?
I'm not sure
So in your cost functions, what do you take into account in order to, or do you tweak it at all in any way in order to make it converge faster with your weights or something like this?
Well, we actually try most of the time to give a full approximation of the Pareto frontier. So let me be very clear that we cannot guarantee that it's the Pareto frontier, but we try to give an approximation. And we don't try to make a choice, say, of the trade-off parameters in advance. We let the user basically see the whole Pareto frontier. Make the choice themselves.
Mm-hmm. And then maybe you have one last interesting but very general question is, what's your take on, is mixed integer programming even needed, or optimization, if we can just use Gen AI to ask the same questions?
I think you're asking to a biased person. So I've been talking about transparency and fairness, but I'm a bit biased because I love, the flexibility that operations research gives to you, and how we come up with tools that are able to incorporate new objective functions. I'm pretty sure that all the new tools that we are seeing in generative AI are going to support our work, but I'm not a believer that is a replacement of our work. I always like to see the combination of the human and the computer. But as I said, I'm a biased person.
Well, we're all biased. Yeah. Okay, good. Then thanks again for the very interesting presentation and the nice discussion.
Thank you, everybody. And if you have any other questions, you have my coordinates.
Yep.
Thank you very much.
Bye-bye. Bye.
Bye-bye.